All right, then welcome to the afternoon sessions. We start with technical talks, and I make very short introduction because we have a lot of very interesting talks and the speakers should have that time. So I say just we have as a first speaker Philipp Haller, who is Associate Professor in Programming Languages at KTH. And please, Philipp, start your talk.
Thank you for the intro, and thanks for the opportunity to give a talk here today. So I will talk about an extension to Dataflow streaming for stateful serverless computing. A lot of words there. Maybe just a few words about myself. So I came to KTH at the end of 2014 and did my PhD at EPFL in Switzerland. And before joining KTH, I actually spent about 9 years on the Scala programming language team, and about 3 years at a startup that's developing frameworks and systems for distributed computing. And in 2019, we were very happy to actually receive an award. It's essentially the highest international award for programming languages software. So we're very proud of that. And my personal focus has been on concurrent and distributed programming. So I've worked on a lot of libraries and language constructs for concurrent programming. And I also created a system called Scala Actors, which was essentially the first widely used implementation of the actor model on the Java virtual machine. So that was even used in production, even though it started as a research project, but it was then adopted by Twitter. So Twitter's core messaging system was actually at some point, not anymore, but at some point it was running the system in production. And actors have also been the main influence for a framework called Akka, which is, again, a very widely used framework for building distributed systems. And if we zoom out a bit more, we see that actors are actually quite commonly used in industry to build large-scale distributed systems. Okay, so for example, the popular Fortnite game is actually built on Akka. And also, you may know that WhatsApp is built using Erlang, which has a kind of built-in actor programming model there. So that's a good story. And of course, if you look at any kind of service that we use day to day, typically these are distributed systems, right? Of course, a lot of these examples, they have to scale to a very large number of users and workloads and so on. And so if you look at how such systems look like, then it's typically a network of interconnected systems, right, where kind of the connections carry events and data and so on. So these are streams of events and streams of data. And each of these gray boxes is actually a distributed system itself, okay? And these are very sophisticated and intricate systems, very large, and they need to be sophisticated mainly due to the requirement of like fault tolerance, right? So for example, like a messaging system like Kafka or a data processing system like Flink, right? Flink was also created with core people here at KTH, or any of these systems, right? They need to be fault tolerant and highly scalable. And now, if you build real systems, then of course it turns out that the services and also the user data, right, becomes scattered across all of these systems, and that's a complexity challenge. Also, if you look at things like handling GDPR compliant requests, right? Then the task becomes quite tricky because we need to be able to find, all the data that's scattered around the system. And sort of to tame the complexity, right, there has been this major trend towards using an architecture called microservices architecture, right? So that's sort of an industry standard, let's say, where basically, a system is composed of microservices, where each microservice is a small service, right, very focused on a single piece of functionality. Now, these distributed systems, right, they're not, they can have issues, right, and even systems that have been developed for a very long time can have sort of disastrous outages. So in December 2020, there was actually a pretty large-scale outage at Google, where you had many of the most widely used services like Calendar, Gmail, Maps, YouTube. They were all down for about an hour. So, of course, failures in such distributed systems, they can be quite catastrophic. In this case, of course, the services are used by hundreds of millions of people, or perhaps even billions. I don't really know. And so we need, obviously, to be able to better handle the complexity and also the resilience, right? And obviously, it seems to be a challenge for companies that employ hundreds of engineers, many of which are specialized in, service reliability and so on. So the reality is, right, that we need to deal with reliability in a very serious way, because computers crash and messages are lost on the network. And we need to be able to scale systems, and both up and down, right? So if the workload increases, obviously we need to have spend more compute resources, ideally sort of automatically. But if the workload goes down, we also want to scale down the resources that are running, right? Because we don't want to pay for something that we don't use. And then we also want to make use, increasingly of edge computing infrastructure. So we want to build systems that are deployed across cloud and edge. So very heterogeneous environments. Some services, of course, also require low latency, low response times, and moreover, we have to deal with systems that handle sensitive data. And some of that data has like a strong regulation with GDPR in the EU, and also CCPA in California and so on. So these are a lot of issues to deal with, and I would claim that we're basically asking a bit too much of the programmers that build these distributed software systems, okay? Because they have to deal with all of these things. So we actually need better programming systems, okay, to construct resilient distributed systems, okay? And so in a recent study that where we have a preprint here from this year, we actually looked at distributed programming systems, and to see, okay, what is it that they're maybe missing, right? What are their limitations? And so we looked at essentially, the different communication patterns that they support. So for example, do they support cyclic communication dependencies or dynamic communication topologies, meaning that communication channels, they can dynamically change, right? And also, can we somehow compose a system in a good way? And also, what kind of processing guarantees do we get, right? Sort of the strongest practical guarantee would be, exactly once processing of events or requests, and so on. And, what we found, and well, I should not forget also kind of properties that we need for different reasons. So for example, these decentralized deployments, that means that there's no central coordinating system that has to coordinate all the interactions. And these decentralized deployments are important as soon as we do edge computing, for instance, right, where the computation happens far removed from a central cloud, for instance, right? So, and then for scalability and data processing, we need different forms of parallelism, task parallelism, data parallelism, and so on and so forth. And so what we found, right, is that essentially there's no current programming system that actually is well equipped to handle all the requirements that we have for our systems, okay? So what ends up happening is that, people connect different systems in ad hoc ways, and then that can, of course, also be problematic because how do you ensure, consistency across systems that have different semantics, for instance, right? So what's our dream, right? So the dream is, of course, that the programmers should only have to write the business logic, essentially, and our stateful serverless system, right, should automate everything else, right? It's a dream, so don't blame me, right? So exactly once processing guarantees, for instance, so that we can reliably, say whether an event has been processed, right? We should be able to scale up and down with demand, and various execution-related properties. So can we support heterogeneous execution? Can we meet the performance requirements, right? Data processing systems typically need to have extremely high throughput, and so on. And also, model serving, machine learning model serving might require low latency, and so on. And of course, finally, for privacy, right? It should not be an afterthought, which it is nowadays, right? So people resort to fairly ad hoc solutions where things are encrypted and the key is thrown away when the data should no longer exist, and so on. So what we want to do is actually have more, from the beginning, some kind of principled approach to handle privacy-sensitive data. So let's just have a look at a simple example, right? The canonical example for a stateful serverless system would be a shopping cart, right? So basically, the scenario is we define our application logic where essentially we have, different processes or microservices that communicate. So for example, we have a cart that needs to communicate with the inventory, right, to see whether an item that was put in the cart, is actually in stock, or how many items, and so on. And we have a system that allows, users to check out and place an order, and so on, right? And so we want to be able to define such an app, and then, deploy it or launch it on a serverless system where, the system ideally kind of automatically provides the necessary compute nodes, according to the demand, and storage nodes, and so on, right? And of course, ideally with the necessary checkpointing and recovery mechanisms, and so on, to do things in a fault-tolerant way. And we might have decentralized deployments, right, with other apps running in the same system, and so on. So if you look at the requirements and challenges, right, certain things we know how to do, but others are more tricky, right? So first of all, building any kind of software application should be done in a modular way. So we should be able to, in a modular way, connect reusable modules, right? That's one thing. Then, we need to have, expected execution semantics, right? So with certain reliability properties. And we also need to support certain communication patterns, right? So the cart needs to query the inventory, which needs to respond, and so on. So we have certain communication patterns. If you look at the serverless system, by the way, one thing I forgot here is like, of course, we need to also meet the scalability requirements. Perhaps the workload increases very much on Black Friday. So this there could be a lot of incoming requests, for instance. Now, on the side of the serverless system, right, we need, for instance, to support handling of privacy-sensitive data, dynamic evolution. So, for instance, let's say we introduce another service, like a third-party service, let's say, that we communicate with. Then that means we need to dynamically evolve the structure of our system, right? Or we might disable certain functionality for certain users if they opt out of some functionality, right? So we dynamically evolve, and by the way, dynamic evolution, definitely we have to do it as soon as we want to deploy a security update, let's say, right? So that's another form of dynamic evolution. And then, decentralization might be another requirement. And so if you look at just one example, the Dataflow streaming systems, okay? Dataflow streaming systems, the two most widely used systems are Apache Flink and Apache Spark by a wide margin, right? And these systems, they actually struggle with some of these requirements. So first of all, they cannot actually support cyclic communication patterns, okay? So that means we would need some kind of out-of-band mechanism for that, where again, who knows how we can ensure the guarantees that we need and so on. Then decentralized deployments are not supported with these systems because they have a central coordination mechanism that orchestrates, the workers and so on. And there's no automation for dealing with privacy-sensitive data, and also dynamic evolution is difficult. Okay, so here we already see, if you just pick one system like Dataflow streaming, we have some severe restrictions. So, in our project, we're working on a system that extends Dataflow streaming to support essentially the missing pieces. And essentially, we are working on a programming model that we call portals. And that programming system essentially introduces two main abstractions. One is called atomic streams. And an atomic stream is essentially a stream of events. And that event stream is discretized into so-called atoms. I will talk more about this in a minute. It provides some very interesting transactional processing guarantees. Okay, so that's let's say, services can communicate using these atomic streams. And then the second one is what we call portals, and that's actually a communication mechanism where different workflows can communicate with each other. Okay, so we build systems as a collection of workflows. Each workflow is essentially a high-performance Dataflow streaming system. But these workflows can communicate in very flexible ways with each other, with certain end-to-end processing guarantees. And what our model importantly supports, that's a principal mechanism, is essentially consistent updates. So we can, certain events, in fact, these atoms, they support serializable state updates, so that, for instance, if we have a GDPR request where a user requests all their personal data to be removed, right? Then it's possible to process an atom that includes that request, and then the system will, due to the processing guarantees, ensure that the deletion is completed before any other event is processed by the system, right? that's an example for a serializable, consistent update. Okay, so now a bit more detail about these atomic streams, right? So essentially, an atomic stream, right, is a stream. It's a totally ordered stream of atoms, and an atom is itself a collection of events. Okay, and the guarantee that an atomic stream provides is that consumers and producers of these atoms, they always process atoms either completely or not at all, right? So if they process atoms in sequence, then they have to completely process one atom before they process the next atom. Okay, and what these streams can be used for is essentially to provide an exactly once processing guarantee. And this means that it's clear that an atomic stream can only be implemented as a distributed system that has, replicated, that has replicas, right, that make sure that, if an atom is indeed consumed from the stream, then, that's durably, persisted in the replicas. So this is And so you can see you can view an atom as essentially a transactional unit of computation, right? So an atom is essentially like a transaction that we execute, and that transaction can itself contain a bunch of events. All right, now the second ingredient, right, of our model is called portals. And portals essentially, like I said, is a mechanism for multiple workflows to communicate with each other, right? And so in like a novel way. So assume we have two workflows, and like I mentioned before, a workflow is basically a data flow graph, okay, where each node is a task or is processing events. And these tasks, they can be stateful. So we have state here, potentially. And a workflow, right, is very similar to what modern data flow streaming systems provide. But now, the sort of novelty is that workflows can communicate using portals. So workflow B can open a portal to workflow A, and then send atoms across the portal, send atoms to workflow A, which processes the atoms and responds with atoms that come out of the portal exit, right? So this is a way to support queries and so on, request reply style communication, but in the form of actually streams of atoms that travel across these portals. Okay, so it's a very flexible mechanism. And so if we kind of revisit our example of the shopping cart, we see that there is actually, we can build the shopping cart using workflows, right? So the inventory could be a workflow, the cart is another workflow, and then these can communicate using portals, right? And so send atoms to each other, and that ensures exactly once processing for each atom, right? And and then since these are workflows, they also have atomic streams that they can use to communicate with other workflows, right? So we can connect workflows together using these atomic streams. Okay? So there's a way to define the application logic in a very well-defined way where there's clear semantics, right? And then we deploy this to our portals runtime system, right, which is a serverless system, meaning that the compute nodes can be dynamically be started and so on, shut down according to the needs. And there's a lot of sophistication in how this is achieved. We have to separate state from computation and so on and so forth. But that's the picture. Now, when do we need to use portals? And the answer is whenever we have requirements that are problematic in current systems, right? So if we have data flow composition, but we also need dynamic communication topologies, that's problematic today, right? We can use portals for that, right? Or if you have iterative computations and we need exactly once processing, that's a tricky case, but we can use portals for that, and so on, right? So we support a bunch of interesting combinations there. And applications, right, could be things where, for example, machine learning, model serving and training. Whenever we have dynamic workflows, we can support distributed transactions using the Sagas pattern. I already talked about serializable updates and so on. So there's a lot of stuff going on, and we are sort of working sort of full steam on this project. So if you're interested in kind of following the development and also experience the first public release, then you can actually sign up for the project launch here. So you can just sign up and you get an email when we have our system released. So takeaways: Dataflow streaming is a great candidate for composable stateful serverless, but it's not great for cycles and decentralized dynamic deployments, okay? And portals extends Dataflow streaming, so we keep the good parts, but we also have atomic streams and portals as a communication mechanism. Thank you very much, and if you have questions,